Right, so welcome to the solutions to the second tutorial sheet, motion in 2 and 3D. You've got a bit of circular motion here as well, and a bit of parabolic motion. First question has a displacement vector r on the xy plane is 15 meters long and directed at an angle theta equals 30 degrees. So that's basically what we have here in the diagram. So we have to find the x component of the vector and the y component of the vector. So this is, remember that when we look at motion, we're trying to break it up into two components, or three components if you have three dimensions. So what we mean by that is there is a component in this direction, which we'll call Rx, and a component up here, which is Ry. Okay, so I've got two components of the vector. This guy here, R, that is 15 meters long, and this angle is 30 degrees. I'll just erase that. Is 30 degrees. Okay, that's our problem. So the first part of the question is asking us to find the x component of the vector. So we're after this guy, the length of that. Well, from trigonometry, you can see here if we have this length r. So it's the length of that vector r is 15 meters long. Then the x components, we can see just from trigonometry that we've got the hypotenuse and the adjacent, so we can use the cos of the angle. So we can say Rx is r cos theta, which is 15 times cos of 30 degrees. And that equals 13, and we must put the units in, 13 meters. So that's our answer. Next part of the question is looking for the other component. Okay, and we just do the same thing, but if you look at the trigonometry of this triangle again, we're going to have to use sine of the angle. So now we have 15 times sine 30 degrees. And that is 7.5 meters. That's our answer. So we have these two components, one in the x direction, so our original vector was 15 meters long at 30 degrees. It can be broken up into a vector pointing along the x-axis, 13 meters long, and a vector in the r and the y-axis that's 7.5 meters long. So the question now is asking us to draw that as a vector with I and j components. So all we have to do then is put these components, so we have to go Rx in the I direction plus Ry in the j direction. So that's our components. So that's 13I plus 7.5j. Too easy. That's our answer. That's how we decompose a vector, or reconstruct a vector from its components. Next question. So two vectors are given by, well, they're depicted there. We're going to do a little bit of vector algebra on this, just as a practice. We've got two vectors. What happens when we add them together? What happens when we subtract them from one another? And what happens when we find the dot product, which is a type of multiplication? So we'll define a couple of things first. This guy here, this number, is what we would call AX. It's the component of A in the X direction. This is the component of A in the Y direction. This is the component of B in the X direction, and this is the component of B in the Y direction. We need those things to do our addition. So over here, we'll start. We're asked to find A plus B. Okay, so to do that, all we have to do is add our x components and add our y components in the different directions. So we actually say ax plus bx in the I direction, I being the unit vector pointing along the x-axis, plus add the components in the y direction as well. And they will point in the j direction. Alright, we just have to put the values in now. Ax was 4 plus bx is -1 in the I direction, The y components are -3 plus 1 in the j direction. So our vector finally looks like 3i minus 2j. There's the answer. The next one's asking us to do a minus b, and in this case all we have to do is subtract the components. So a minus b is equal to the x components subtracted from one another in the I direction plus the y components subtracted in the j direction. And we get a vector then, that is we put the components in. Ax is 4, bx is, so minus -1 in the I direction, plus ay was -3 minus by, which is 1 in the j direction, which comes out to be 4 minus is 2 minuses is a plus, so we get 5i, and we're going to have minus 4j. And that's our answer. Pretty straightforward if you know that it's just adding or subtracting the components. The component being these values at the front, ax, ay, of the unit vector. C is asking for the dot product. So an easy way of doing that in component form, as you saw in the lectures, is just to multiply the, I'll just erase that, sorry, that's a mess, is to multiply the components. Okay, so we get ax bx plus ay by. And you can see they're just numbers, so we're going to get a scalar as the answer, which is why the dot product is called the scalar product. So let's put the values in. Ax is 4 times -1 plus -3 times 1 comes to -7. That's a number. So that's our answer. Comes out as a number. Remember also that the dot product of two vectors can be given as the magnitude of A times the magnitude of B times cos of the angle between them. Sweet. Right, so this question states that we have a car which has an initial velocity depicted by this expression here. You can see that it has three components, vector components, 4 in the I direction, -2 in the j direction, and 3 in the k direction. So it has the individual directions have their own component, vector component associated with them. Remember, we're looking at motion and we break it up into our three directions in the x, y, and z direction, denoted by I, j, and k. 4 seconds later, so after some period of time, it has a new unit vector, a new velocity vector, with different components in the I, j, and k direction. So the change in the velocity vector is going to give us the acceleration as a function of time. So the first question is asking, what's the car's average acceleration in unit vector notation? So we have this vector, and we know that to find the average acceleration, we just find the change in the velocity over time for the two different points where we've measured the velocity. And we can do that individually for the x, y, and z directions by looking at the different components of the velocity. Right, so I can write that down and say that it's the rate of change of the velocity vector as a function of time. Okay, so we're going to have some change in the x direction as a function of time, and that's going to point in the I direction. We're going to have some change in the velocity, the y component of the velocity vector as a function of time, and that's going to point in the j direction. And we're going to have some change in the velocity in the z direction, and that's going to be denoted by the unit vector k. Right, so now all we need to do is see what is the change in each one of these velocities components. Well, you can see that, let's look at the x. We started off as minus 2 in the I direction, and we end up with 4 in the I direction. So our change is minus 2 minus 4, and it took 4 seconds to do it, so the time is 4, and that's in the I direction. Let's look at the the j direction now, or the y direction. We started at minus 2j for velocity, and we end at minus 2j. That says that there's 0 acceleration in the y direction. So it's plus 0j. And for the final component, we started at 5k and we ended at 3k. So our change is 5 minus 3. Again, divide by the time taken, which is 4. And that's going to be in the k direction. We do the maths on that, and we're going to get minus 1.5 in the I direction and plus 0.5 in the k direction. And that's our final vector. We can do a few things with that. We can find out what the magnitude or the length of that vector is. That's what the next question is asking us to do. And this just comes from Pythagoras. So if we want to find, want to save the project, cancel. If we want to find the size or the magnitude of that, then we can use Pythagoras. We say the magnitude or the size, it's denoted by these lines, either side like that. That means the magnitude or the size. It's just going to be, the square root of the components. So it's going to be the square root of ax squared plus ay squared plus az squared. Okay, so we can put those values in. We already know what they are. It's minus 1.5 squared. This was 0. And az squared is 0.5 squared. That comes to a value of 1.6, and remember our units, meters per second squared. That's our answer. So the final part of the question is asking us to find the angle between the average velocity and the positive direction of the x-axis. So the way we do that, remember, is there's a relationship tan theta, theta is what we're looking for in this case, is equal to az over ax. Okay, so therefore theta is tan minus 1. That's the opposite of finding the tan, it's finding the inverse tan. Az over ax, so az is 0.5 over negative 1.5, and that comes out to be tan minus 1 of 0.5 divided by 1.5. Hey, let's just skip a step there, I'll just erase that. We can just plug that value into our calculator actually, and that's going to give you an answer of minus 18 degrees or 162 degrees. Now if you look at the sign of the components, so this component here, the I component, is a negative, so it's going to be, the vector's pointing in the negative direction in the I and a positive in the k, therefore it must be in that second quadrant somewhere. So it has to be this value here. That's how we differentiate the which value we choose there. Cool. Okay, so here we have projectile motion problem, pretty typical one. There's only a difference here in that the projectile is being fired horizontally at a height above flat ground. So the first thing I would do with projectile motion problems is draw a diagram of what's happening. I'll just change my color there. So I've got a cannon gun like this, and it's pointing, or it's firing a projectile and here's the ground. It's firing a projectile like this that's going to hit some target on the ground. And the displacement, so that in the x direction, delta x is the range of that projectile. We're told in the problem what this distance is. I'll call that delta y. We're told that if we say upwards is positive, then the displacement downwards is negative 45 meters. Okay, so that's a bit of information that we have. What other information do we have? Well, we can say that theta equals 0 degrees. We're firing horizontally only. This means that all of the initial velocity goes into the horizontal direction, and so the initial velocity y is 0 meters per second. That's very important for the problem. It allows us to solve it. The acceleration in the x direction, because there's no wind resistance, is 0. The acceleration in the y direction is going to be negative 9.8 g. Meters per second squared. Hold on. Wrong units. It should be meters per second squared. Okay, so that's some information that we have. What other information do we have? Well, that's pretty much all we've been given in the problem. So in question A, we are asked to find how long is the projectile in the air. So t equals what? So we know what we have. We have this group of variables over here. How do we use those to solve for t? What connects them? Well, it turns out that you have this equation that's delta y. So we're looking for motion only in the y direction now to find out what the time is. Delta y equals v naught y, velocity in the initial component in the y direction, times t plus at squared on 2. That's nice. We can get rid of that because our v naught y was 0, and we end up with, so therefore, delta y equals at squared on 2. We're trying to solve for t here, so we're going to have to rearrange it a bit. So 2 delta y divided by a, that's just taking the 2 from here and putting it over there, taking the a and putting it over here, equals t squared. Therefore, t equals the square root of 2 delta y over a. We can now put some values into that expression. 2 times delta y is minus 45, and the acceleration was minus 9.8. And that comes out to be, plug it into my calculator brain, 3.03 seconds. Excellent, we've answered the first question. So that time, incidentally, is going to be the same time. So the time taken for it to go from here down to here is the same as the time. Sorry, I'll just draw that on the diagram. The time taken to go from here to be fired to get down to here is the same as the time taken to go across that way. Okay, so time is going to be the variable that we're going to use. So this makes the next problem quite easy. At what horizontal distance from the firing point does it strike the ground? We know this acceleration in the x direction is 0. Okay, we know the time now to go from the here down to here. So that's 3.03 seconds. And what we're looking for is the horizontal displacement delta x. It's really easy. Velocity equals distance over time, so it's going to be, well, we know our initial velocity as well, so I'll write that down. V naught in the x direction. Hold on, I'll just, again, just erase this to make it look a bit better. Eraser, get rid of this bit. Okay, we know that that's 250 meters per second. We're told that right at the start, and we're trying to find delta x. So velocity, which is v naught x, equals distance, which is delta x over time. Okay, so just rearrange that for a delta x. Therefore, delta x equals v naught x times t. We've got those values, 250 times 3.03, and that comes to be 758 meters per second. Meters, sorry. I'll get there eventually. It's meters. Excellent. So that solved that part of the problem. The final part of the problem, C, is trying to find, let's scroll back up again so we can see it. What's the magnitude and vertical component of the velocity? So we're looking for Vy, the final velocity, Vy as it strikes the ground. So we need to find V naught, we've got V naught Y, that's 0 meters per second. We're looking for Vy, the final velocity. And we've got T is 3.03. We don't really need that, as we'll see in a second. We have the acceleration in the y direction as minus 9.8 meters per second squared. And we also have the displacement in the y direction was minus 45 meters. That's all the information we need to solve this. We have an expression then, so you look at what you have and what you're looking for. You're looking for this guy, so you can find the equation that works, and it's this one. This is a list of equations of motion, v naught y squared plus 2a delta y. So therefore Vy equals square root of v naught y is going to be 0, so that bit disappears. So we're just going to get 2a delta y. Okay, we can put those values in. 2 times negative 9.8 times negative 45. And that comes out to be 29.7 meters per second. Solved. Okay, we have another projectile motion problem. This time you're going to have to find out what your horizontal and vertical components of initial velocity are. We're going to use those to find out what the horizontal and vertical components of the displacement at the final point where it hits the ground again, or after a given amount of time. Okay, so let's do that. The first thing I would do here is start by drawing a drawing. So we're shooting this thing off like this, and we're shooting it off at an angle theta equals 40 degrees. And the magnitude of the velocity, so the magnitude of v, is 20 meters per second. Okay, so we're shooting it off at some angle, with a magnitude of velocity of 20 meters per second at an angle of 40 degrees. So that's the first thing we do, is draw the drawing. Now, we can easily answer question A and B now. We ask for the horizontal and vertical components of the initial velocity. Remember that the horizontal component Vx is just the magnitude of V cos of the angle that it makes to the x-axis. That's going to be 20 times cos of 40. Make sure your calculator is in degrees. If you put 40 in there and you've got your calculator in degrees, you're going to get the right answer. If it's in radians, you'll find the cos of 40 radians, which is different. So this will be 15.3, and it's meters per second. B, Vy, remember, we just have to find the sine of the angle. This is just from trigonometry, guys. 20 times sine of 40. And that's 12.9 meters per second. Excellent, those two are solved. So now, C. At t equals 1.10 seconds, find the magnitude of the horizontal displacement. So at some point in the trajectory, we want to find how far has it gone. So it may not be the end of the trajectory, but at some point, t equals 1.0 seconds after the launching, where is it going to be horizontally, and where will it be vertically? Okay, so it turns out easy in the x direction because remember again, a in the x direction is 0 for projectile motion. There's no acceleration. So the velocity is going to stay constant. So therefore, velocity equals displacement over time. Okay, so that is rearranged. We're going to get delta x equals v naught x times t. Put some values in for that, which we already have. We worked out up here that the velocity, initial velocity in the x direction is 15.3 meters per second. Sorry, just to I'll get rid of the units for now. I only put the units in at the end, makes it a bit easier. And the time, 1.10. And I get an answer that is 16.8 meters. So we've gone 16.8 meters in the x direction. Now remember, our motion for projectile motion is 2 or 3 dimensional, so we also have to find out what the displacement is in the vertical direction, so we have to treat it differently with a different equation of motion. Okay, so what do we have? We have the time equals 1.10 seconds. We have the acceleration in the y direction. It's minus 9.8 meters per second squared. We have the velocity, initial velocity in the y direction. We worked it out in the second problem, is 12.9 meters per second. So we have those things. And what are we looking for? Well, we're looking for delta y. So we look at what we have, what we're looking for, and that's going to help us with the connection. Which is the equation of motion that's going to work? Well, this one here contains all the information we need. V naught y t plus at squared on 2. So if we put in some values for that now, we've got 12.9 times 1.01 plus negative 9.8, so watch the signs here guys, times 1.01, and watch the squareds as well. That's another reason why people make the mistake. Divide by 2. Punch that into your calculator and you'll get an answer that it's about 8.3 meters. So have a think about that answer. After a given time, if I'm going at an angle less than 45 degrees, then my x component, this guy, should be larger than this guy. I'm going to go further in the x direction than I will in the y, and that's kind of what works. Okay, so just check that your answer makes a bit of sense. So this question is a question of uniform circular motion. So what I mean by that is you've got the Earth sitting here like this, and it's got some radius, the radius of the Earth, and you've got your little satellite whizzing around it at some other radius, which is 640 k's longer. So what's going to happen here is you've got this thing in uniform circular motion. It's got some velocity. It's always a tangent to the circle or the orbit that it's going around. So v is like this. Now the length of that vector isn't changing, but what's actually changing with the vector is its direction. So if you want to alter a vector, a velocity vector at all, you have to have an acceleration vector, and it turns out that points towards the center this way. So that's the acceleration vector. It's called the centripetal acceleration. So if you want to change the length of a velocity vector or the direction, you have to have an acceleration vector to do that. So with uniform circular motion, you're just changing the direction using the acceleration vector. Okay, so we need to solve this problem now. You're not told in the problem, but the radius of the Earth is 6.37 by 10 to the 6 meters. Okay, you're also told in this case that the orbital period is 98 minutes. That's not a useful unit, so we need to convert that using our bridge method. We know there's 60 seconds in a minute. Cancel those algebraically, and we get 98 times 60 seconds, which is 5,880 seconds. Okay, so we've got some information here to solve now. The orbital radius, r, is going to be 6.37 by 10 to the 6 plus this extra 640 kilometers, so 640 by 10 to the 3 meters. And that comes out to be 7.01 by 10 to the 6 meters. So that's our orbital radius, that's our orbital period. So if we want to find out the velocity, well, it's just velocity equals distance over time, or speed. The distance is just, in one period, is just 2 pi times the radius of the orbit, divided by the period of the orbit. We've got some values for that now. We can just say 2 pi times 7.01 by 10 to the 6 divided by 5880. What's the value for that? When we punch that into the calculator, we get 7.49 by 10 to the 3 meters per second. So that's quite fast. But that's the answer. That's the sort of speed it takes to keep us in orbit. The next part of the question is asking for the magnitude of the centripetal acceleration of the satellite. We know it points towards the center, but how large is the acceleration? Well, we know that the centripetal acceleration's magnitude is just the tangential speed v squared divided by the radius of the orbit. We can put those values in now, 7.49 by 10 to the 3, divided by the radius, which is 7.01 by 10 to the 6. The answer there, oh sorry, I've got a squared term here, remember? I almost made a mistake. That comes to 8 meters per second squared. That's the acceleration. Well done, guys. If you got those answers, that's very good. If you didn't, please talk to me, talk to your tutors, and do more practice problems, and I'll see you next time.